So in the last session, we introduced the indefinite integral. So, and we discussed that how an integral of a function can be found by the um, standard results of integrals, which are based on the results from the derivatives. Integral is nothing but the antiderivative. So based on the results from the derivatives, we find the integral. And I gave a big list to remember. And then we did quite a few examples of integration by reducing to standard forms. And then we discussed integration by substitution. And we discussed number of results by substitution, and then we discussed some problems based on substitution. This is what we did last time. Now, today's topic, of course, this is not going to be an in-depth treatment of integrals. I am just covering whatever is required from the gate point of view. For indefinite integrals in depth, of course, you should, if you want to review and practice, you should go back to your school or intermediate level mathematics books and just review some questions. Of course, I'll give you some assignment which will not be like the usual ones which I give for IIT JEE type of preparation at a higher level. It will be something that you can reasonably do. So now, for today's class, we begin with integration by parts. So we covered integration by reducing the integrand to standard forms. Then we completed integration by substitution, and now we will do integration by parts. So let's begin. This is usually done for a product if the integrand is a product of two functions. So if u and v are two functions of x, then integral of u v dx is u integral of v dx minus integral of the derivative of u multiplied by the integral of v dx, whole integral. So how do we remember this? U is called as the first function, v is the second function. So the integral is remembered like this: first function into integral of the second minus minus the whole integral of the derivative of the first times integral of the second. So this is how we remember this integration by parts. Of course, this can be proved, and in preliminary texts on calculus, integral calculus, this proof is very readily available. But for us, we just go by this formula. First function into integral of the second minus derivative of the first into the integral of the second. Now, how do we now, if there is a product, how do we identify first and second functions? How do we identify first and second functions? Does anybody remember? Whoever is present today? How do we identify the first and the second functions? No one remembers? Are you all able to hear me?
Yes, sir.
Yeah, tell me. So first function is u, second function is v. Which in the product, which should be u, which should be v? So consider the acronym. It's ILATE. Okay. I stands for inverse trigonometric functions. L stands for logarithmic functions. A stands for algebraic functions. T stands for trigonometric functions. And E stands for exponential. Do you remember now? Okay.
Yes, sir.
Now, of the two, okay, of the two functions, whichever comes first in the sequence ILATE shall be considered as the first function. And the other one will be considered as second. Okay. Now, that is one. This is one rule. Now, second is, if both are algebraic, choose first function as that whose derivative is simpler. Okay. And if it is trigonometric, generally this kind of case we don't usually get, um, but there's a rule we should know. If both are trigonometric, choose second function as that whose integral is simpler. Okay. Suppose there is secant x and cosecant square x. Integral of cosecant square x is cot x, but integral of secant x is log mod secant x plus tan x. So choose cosecant square x as the second function. That will make integral easy. This is by practice you get. If there is only one function, whose integrand, whose integral is unknown, choose that as the first and one unity as the second. So let's apply this to some problems and see. So okay. So examples we'll take for practice and then we'll move forward. First one, integral of x times log x dx. We need to evaluate this integral. How do we do that? Now there is x, this is log x. Now we go by I late. Here we have a purely algebraic and here we have a logarithmic. Okay. So we have logarithmic and algebraic. So logarithmic should be taken as the first function. So we choose this as the first function, u, and this as the second function. Okay. So now integrating by parts. So integrating by parts, the integral I will be first function log x into integral of the second minus integral of the derivative of the first into the integral of the second. So we get log x into x square upon 2 minus integral of derivative of log x is 1 upon x and integral of x is x square upon 2. So this makes it easy. So I is half x square log x minus half integral x dx. So this is half x square log x minus half x square upon 2. And finally add plus c. So if we take this x square upon 4 common, we get 2 log x minus 1 plus c. Okay. So this is integration by parts. Once you identify first function, it is first function into integral of the second minus integral of the derivative of the first into the integral of the second, the whole integral. Okay. So this is standard one. Sometimes we may have to do it twice. Let's do this. Integral x square times cos 2x. Now please tell me which one will be the first function and which one will be the second function.
So x square will be the first one.
Very good. Because we have algebraic and trigonometric. So the algebraic has to be the first function. And this is trigonometric. So this is the second function. So now integrating by parts. So I'll not write all these steps again. So first function into integral of the second minus integral of the derivative of the first. One more time. I'm just writing for the second problem. From next problem onwards, I'll directly write the integral. Derivative of the first multiplied by the integral of the second. So we have x square. Integral of cos 2x is sine 2x upon 2 minus integral of 2x times integral of sine 2x upon 2. So 2 and 2 cancels. Half x square sine 2x minus. Now again you get x and sine 2x. Again we have to do integration by parts. Again integrating by parts. Half x square sine 2x minus full brackets, a big bracket, first function into integral of the second. Integral of sine 2x is minus cos 2x upon 2. Okay, this is the integral of the second function minus integral of derivative of the first function. Derivative of x is 1 and integral of the second is minus cos 2x upon 2, all brackets. So we have half x square sine 2x minus times minus is plus x upon 2 times cos 2x minus into minus plus times minus is minus. We get half into integral of cos 2x is sine 2x upon 2. So in effect, we get this as 1 upon 4. So 1 upon 4 times sine 2x plus c. So this is integration by parts. So of course you can collect the sine 2x terms and cos 2x terms separately and simplify further. But this is the case where there is integration by parts used twice. All right, next we have some standard results. Okay, one more we will do, one more. And then 2 on integrate x times tan inverse x dx. So which is the first function and which is the second?
So tan inverse is the first function.
Very good. So there are two functions. X is algebraic. So we have inverse trigonometric and algebraic function. So x will be the second function and tan inverse x will be the first function. So integrating by parts. First function, what will it be? X. No, sorry. First function is tan inverse x times the second function integral dx minus integral of the derivative of tan inverse x into integral of x dx. So this is tan inverse x times x square upon 2 minus integral of derivative of tan inverse x is 1 upon 1 plus x square times integral of x is x square upon 2 dx. So we have half x square tan inverse x minus half integral. Now we have this x square upon 1 plus x square. How to solve this one? To solve this, we add 1 and subtract 1. When we do that, we can split this as half times integral of 1 minus 1 upon 1 plus x square dx. This is now in standard forms. We have standard results for that. Integral of 1 is x and integral of 1 by 1 plus x square is tan inverse x. Plus c. So we can simplify half times x square plus 1 tan inverse x. I am adding the tan inverse x terms minus half x plus c. So this is integration by parts with an inverse trigonometric function and an algebraic function. So we did algebraic logarithmic, algebraic trigonometric, algebraic inverse trigonometric. Now let us do cases where there is no second function, meaning there's only one function. So evaluate integral log x. This is log to the base e. So integrating by parts solution is integrating by parts taking 1 as the second function. Taking 1 as the second function. So I is integral log x dx, which is first function into integral of the second minus integral of derivative of the first into integral of the second. Now, I is x times log x minus integral of 1 upon x times x dx. So 1 upon x times x is 1. So integral of 1 is x plus c. So integral of log x is x log x minus x. So this I have given as one of the standard results. One of the results that we need to remember. Okay. An integral of sine inverse x. I would want you all to do this and give me the answer. Please do this. I'll give you 2 minutes time. Those of you finished, you can raise your hands or put message in the chat. Of course, you will not be able to write the solution, but just say that you have completed. Good. Good. Okay. So I'll tell you the solution. I think most people must have got stuck with the second integral. So integrating by parts, taking 1 as the second function. So I integral. So all right, I'll write this integral sine inverse x into 1 dx is first function into integral of the second, which is x, minus integral of the derivative of the first, 1 by under root 1 minus x square into integral of the second, x. So I think most of you must have got stuck here. How to do here? This is simple. This is integration by substitution. What I'll do, I'll multiply and divide by 2. What is the derivative of 1 minus x square minus 2x? So I'll take this minus sign inside. So I've taken the minus sign inside, multiplied and divided by 2. So I get this is derivative f dash x by under root f of x, that form. Or you substitute 1 minus x square as t, minus 2x dx will become dt upon root t. Under root t integral with respect to t is t power half upon half. So 2 under root t. So you get this as, by the standard result, 2 under root 1 minus x square plus c. I'm just using this standard result. Let me see where it is. Yeah. The fourth one here, f dash x upon under root f of x dx is 2 under root f of x plus c. So integrals is generally we get by practice. It is not by just memorizing the procedure. We need practice. So this is a standard one. X sine inverse x plus under root 1 minus x square plus c. This is the integral. Now there are some other important integrals like okay, one of these 10 standard forms that I gave, we'll do one of them. Yeah, one of these, the last 3, one of them we need to do. Okay, so let us choose a 8th and 9th. We can do by integration by parts. So this is, these integrals are very important what I'm doing, because in application of integrals, This is nothing but, y is equal to under y square, x square plus y square equal to a square. It's circle. So y will be written as under root of a square minus x square. So this forms a semicircle. And there are many problems of area and volumes bounded by a semicircle and hemispherical regions. You get integrals of this type, and it's extremely important, this one. So take integrating by parts. Taking 1 as the second function. So I is integral of under root of a square minus x square dx. Under root of a square minus x square times integral 1 x minus integral of derivative of the first minus under root of a square minus x square times minus 2x. Sorry, 1 upon 2 root a square minus x square multiplied by the derivative of a square minus x square is minus 2x times integral of the second. So we get x under root of a square minus x square. Now we get minus of 2 cancels, and we have minus x square by root of a square minus x square dx. Again, like previously, we added and subtracted 1 in the previous problem, but here, because of a square available, we'll add and subtract a square. This makes it easy. We take the first 2 terms together and divide by the denominator. We get integral of under root of a square minus x square dx plus minus of minus plus a square times dx upon under root of a square minus x square. So this is x root of a square minus x square minus I. This is an integral which got repeated itself while in the process of integrating. This got repeated within the integral itself. So we can replace this with I plus a square, and this is a standard result, sine inverse x upon a. This is sine inverse x upon a. So taking this to the other side, we get twice of I is x root of a square minus x square plus a square sine inverse x upon a. So I will be x upon 2 under root of a square minus x square plus a square upon 2 sine inverse x upon a. Okay, so that's the result. Now let's prove the second result. I hope you are taking down along with me. Next, integral root of x square plus a square. Of course, for this, assuming that this previous integral is known, yeah, see, assuming that this integral is known, 6th and 7th. We are doing 8th, 9th, 10th. Okay. So 6th and 7th is direct. It is, of course, if we integrate this one, if you differentiate the right hand side, you will get the left hand side. You can cross check that. So this one of the standard forms. We get this integral by substituting x as a secant theta. And then we'll be able to solve this one. And this as x equal to a tan theta. And then we'll be able to solve this. So let's try one of the lower three, 8, 9, 10. But those have to be remembered, memorized. Huh? But suppose you get stuck in a problem like that, and there are problems like that in application of derivatives. So integrating by parts, this is the solution. So taking 1 as the second function. So integral of the second is x minus integral of derivative of the first times integral of the second. So this is x under root of x square plus a square minus of, we have x square by root of x square plus a square. So solution is easy. Add a square in the numerator and subtract a square and take the first term as x square plus a square. So we get x under root of x square plus a square minus integral root of x square plus a square dx plus a square times integral dx upon root of x square plus a square. So this is I. So bring this to this side. So 2i is equal to x under root of x square plus a square plus a square times, this is log mod x plus root of x square plus a square. All right. So therefore I will be x upon 2 under root of x square plus a square plus a square upon 2 log mod x plus root of x square plus a square plus c. That is what was the result. So this is how you get integration by parts. Now there is some trick in some important results within integration by parts apart from these here. These are some important results. Rahul, you're raising your hand. Do you have a question?
Sir, no, sir. It was previously raised. I didn't go.
Okay. So this is, again, the first one is useful, very useful. Second one is an extension of the first. And these two, it's a combination of exponential and trigonometric. So if you use I late, you will use e power ax as the second function, and sin bx as the first function, and you can solve. And this, I think you would have done it. I will show another method today. Let's first take the first one. This one, see, integral e power x times a function plus its derivative. This is integral e power x f of x dx plus integral e power x f dash x dx. So take this function, integrate by parts. So integrate this by parts, taking f dash x as the second function. So what do we get? We get integral e power x f of x dx plus integral of, so this integral, so first function into integral of the second minus integral of the derivative of the first times the integral of the second. So what do we get? Integral e power x f of x dx plus e power x, and integral of the derivative is the function itself, minus integral of e power x f of x dx. So the integral cancels itself. So we get this as e power x times f of x. So this is a very important type of a function, integral. Many times in objective bits, you can directly substitute the answer just looking at this function. If you're attentive to it, you will be able to do that. We'll take simple examples on this. So we covered how many today? 7 integrals today, more. So examples on this. Eight. Okay, integral of e power x into cos x minus sin x. What should be the answer?
E power x cos x.
Yes. So this is e power x into cos x f of x plus the derivative of cos x. All right, f of x plus f dash x. So this integral is e power x times f of x. So that is e power x times cos x. All right. Integral e power x secant x plus secant x tan x. Answer?
Power x secant x.
So e power x secant x plus c, direct result. Let's do now, little trick. E power x into x upon 1 plus x square, 1 plus x the whole square. Yeah. E power x into 1, e power x into x upon 1 plus x whole square.
E power x into 1 plus x plus c.
E power x into?
1 e power x into 1 plus x plus c.
No, rethink your answer. You might have got it right, but what you are saying is wrong. I add and subtract 1. Then I simplify this e power x. I divide by the denominator. The first term I'll get 1 plus x. The second term I'll get minus of 1 upon 1 plus x, the whole square. So this is what I get. So this is, if this is taken as f of x, derivative of this is minus 1 upon 1 plus x, the whole square. Okay. So this is e power x upon 1 plus x plus c. This is the answer. Shankar, what you were saying is e power x into 1 plus x. It is e power x divided by 1 plus x. Okay. Integral 1 upon log x minus 1 upon log x the whole square dx. There is no e power x term here. However, this is one of the same problems, exactly like the previous one, just that we need to substitute. Substitute log x is equal to t. This gives us x is e raised to the power t. This implies dx, the differential of x, is derivative of e power t is e power t dt. Therefore, the integral is 1 upon t minus 1 upon t square times e power t dt. Now this is in the form e power x into f of x plus f dash x. So if this is taken as f of t, this is f dash t. So f of t plus f dash t, you should get, not minus. So this minus sign is included within the derivative. So this becomes e power t upon t plus c. Now e power t is x and t is log x. So this is the result. Okay. I hope you are taking down along with me. Don't think that, okay, I have done these in the past. I'm purposely making you solve some things. Why? Because you need to work your mathematics in your mind. And some of these integrals, I'm choosing very carefully which ones you should practice, which ones you should not. Now, once like this e power ax sine bx and e power ax cos bx. You can memorize this, or you can do integration by parts. On doing integration by parts twice, I repeats itself, and then you can bring it back to the left hand side and simplify. But I'll give another very efficient and elegant method to solve this. So evaluate integral e power ax sine bx and integral e power ax cos bx. Okay. Now I'll do like this. Let I1, the first integral, be integral e power ax cos bx dx. Yeah, I missed a dx. And let I2 be integral e power ax sine bx dx. Let I, capital I, be I1. This is I1 plus iota I2. This iota is the complex unit. Okay. What happens? This becomes integral e power ax cos bx dx plus integral I times integral e power ax sine bx dx, which is same as integral e power ax cos bx plus I times e power ax sine bx whole dx. This integral of e power ax times cos bx plus I sine bx dx. Okay. What is this? By the Euler's formula for complex numbers, this is e power I bx. Since the Euler's formula for complex, it's Euler's identity for complex number, e power I theta is cos theta plus I sine theta, right? Now, this becomes integral of e power a plus ib times x dx. This is e power ax type integral, which is itself, the integral is itself upon the coefficient. Okay. Now, that's all. Integral is done. And at a go, you can get both the integrals. Now it's a matter of the complex simplification. Simplification of the complex numbers. So numerator is e power ax into e power ibx, and the denominator multiply and divide by the complex conjugate. So we get e power ax into cos bx plus iota sine bx times a minus iota b by, this is a plus ib to a minus ib is a square plus b square. So this is a e power ax by a square plus b square times a cos bx, a cos bx, plus I times a sin bx, then minus I times b cos bx, product minus I square is plus 1. So you get plus b sin bx. Now split the imaginary and real parts. We get e power ax upon a square plus b square times a cos bx plus b sin bx plus iota times e power ax upon a square plus b square times a sin bx minus b cos bx. That is I. So I we know is I1 plus I times I2. So we get I1, which is integral e power ax cos bx dx, which was the original integral, is this e power ax by a square plus b square times a cos bx plus b sin bx. Very easy way to solve. Very easy way to solve. It's just a matter of um, algebraic manipulations, but there is no deeper concept involved. Just very, very simple way we get the solution. So I had C both sides. So that's what is the result. If we see, this is the result. A sin bx minus b cos bx plus c. I didn't use integration by parts, anything. I just used the concept of complex numbers and solve this problem. Okay. So we'll end with the integrals here. I will give you a exercise set for you to solve for practice, just so that you're good in grips with solving, evaluating the indefinite integrals. They are all of the integrals that you can think of fall within one of these three categories: reducing to standard forms, then integration by substitution, and integration by parts. All other integrals can be brought down to one of these three methods. There is no other method as such in indefinite integrals other than these three. All others are derived methods. So there may be many other functions, rational functions, irrational functions, other trigonometric functions. They're all based on this. All right. So this much is sufficient for from the gate point of view. Okay. Now, what we go on is to the very important topic, and on this we get a lot of questions. So now we come to a very important topic. This is the definite integral. First step, we need to understand the concept of definite integral. Before we go forward to um, just applying formula, indefinite integral is antiderivative, and we found methods to get the antiderivative. Finding the derivative of a function is straightforward. You have certain rules, sum rule, product rule, quotient rule, chain rule, so on. And we keep applying, and there are standard results for it. We keep applying straightforward, you get the derivatives of functions. To find antiderivative, it's a reverse intuitive process, and the standard methods are there. But what is definite integral? To understand definite integral, first, let us consider a regular polygon inscribed in a circle. Circle of radius r. Okay, so let's consider a circle. And there is a polygon I'll not put this line. I'll just mark the center. And let's say there is a polygon inscribed within this circle. We can take maybe a hexagon. So I'm joining. Okay. This is an hexagon, regular hexagon. So all the sides are equal, of course. Now I join the vertices to the center. What I get is an isosceles triangle. Of course, in the case of a hexagon, it will be equilateral triangles. These are radius r. All of them radius r. Assume that there are n sides. Each of this angle will be 2 pi upon n. Okay, each of this angle is 2 pi upon n. 2 pi upon n. Because polygon, regular polygon of n sides, if we consider. Now, what is the area of the polygon? Area of this polygon. Now, area of this polygon can be taken as area of the polygon can be taken as n times, there are n triangles. Here in this case, there are 6 hexagons. So 1, 2, 3, 4, 5, 6. So n times area of each isosceles triangle. Right? Because all the triangles are equal. So n times. Now area from trigonometry, if you know 2 sides of a triangle and an included angle between them, AB and angle C, then half AB sine C is the area. So this is half R times R, half AB, and sine of the included angle. So this is the area of the regular polygon inscribed within the circle of radius R. Okay, so this is area of the polygon of n sides. Now, what happens because of this polygon? Now, this area is the area, the difference of the area between the polygon and the circle, isn't it? This area marked in red is the area outside the polygon but within the circle. Now, as the number of sides increases, as the number of sides increases, this area keeps reducing, isn't it? All right. Suppose you have 4 sides, a polygon, a circle with a square, and circle where we have a circle with a square inscribed in it. Then the amount of area, the difference of the area is quite large. Now, as the number of sides increases, this area reduces. Now, as n tends to infinity, what happens? Let us study that. Limit n tends to infinity, n r square upon 2 sine 2 pi upon n. Now, as n tends to infinity, 1 by n tends to 0, isn't it? So r square by 2, keep it as it is. This is sine 2 pi upon n upon 1 upon n. So this is sine ax upon x as x tends to 0. That is equal to a, the coefficient. So you get r square times r square by 2 times 2 pi, which is pi r square. So limit n tends to infinity, an is pi r square, which is equal to the area of the circle. Okay. So this is the area of the circle. How did we find the area of the circle? We added. All right. The question now, what is integration? So in this case, how did we find the area of the circle? Answer. We added the areas of triangles as they tend to infinity. Okay, we added the areas. This is called as the integration. Integration means adding up. It means adding up. So this is the concept of integration, which we have used for finding the area of a circle through the means of a regular polygon. All right. But how do we get that integral f of x dx? Okay. So here is the concept of integration. Very, very important. I'm going by the fundamentals, because once you understand this, you will get a full visual picture of what is integration. Okay. So concept of this integral, what is behind it? What do we mean by integral a to b f of x dx? So let us take a function f of x. So let's say we have a function like this. This is y equal to f of x. Or yeah, uh, uh, it's okay. We can take a increasing and decreasing function, or we can take a decreasing function, any way we like, doesn't matter. Now let us say there are 2 points a and b on the x-axis. All right. Now what we do, we divide. We want to find the area bounded by these lines. This is x equal to a line, x equal to b line, and this curve y equal to f of x with the x-axis. Now let us divide. Let us divide. Yeah. Let us divide this whole interval into n parts. Okay, let's divide this into n parts. Now, what I'll do now, these each one will be, let us say, this is a0. A0 is a, and this is a1. This is a2, so on. This is ai, and so on. B minus a, of course, I don't want to commit that these are equal intervals as of now. All right. This will be a n minus 1, and the a n will be equal to b. Now just look at this. The way I plot, I'll replicate the exact image again. Sorry. Okay. I'll replicate this. I've replicated this. But for the first one, just look at it. In this whole subinterval, so I've divided this interval a b into n subintervals. When I divide into subintervals, and within each subinterval, I will take the lower value. the lower value, whichever is the least value of the function, I am taking that, not the highest value. The lowest function value, I am taking that. And now I calculate this area. All right. This entire area, I am plotting the whole thing. This we denote by L, this particular area. Okay. Now we call this L as summation of this distance is delta xi into f of, I would say, f of ci on each ith interval. All right. Now I equal to 1 to n, where ci is the point of minimum in the subinterval. All right. This is called as the lower integral sum. Now, obviously, as n approaches infinity, this value, this difference that we see here of between the actual area and the approximated area or the shaded area, that will minimize. So then we get this area under this curve. So now look at the other way around. Now I choose the maximum of the function value within the subinterval. What I get? I get an area which is larger than the actual area. However, this is also an approximate calculation of the area under the curve. So this entire shaded portion is the area. Now this area is your upper integral sum, u. This is also sigma I equal to 1 to n intervals. Now we can write this as f of c, capital Ci, or maybe we can mark Ci bar delta xi. What is delta xi? The interval, subinterval length. The subinterval length. Now, this is the upper integral sum. Where C is the point of maximum in the subinterval. Now, as delta xi tends to 0, that is, as n, the number of subintervals tend to infinity. Okay, n is the number of subintervals. In the traditional definition, the maximum width of the width of the largest subinterval, that tends to 0. So then what happens? This is limit n tends to infinity or delta x tends to 0. It's the same thing. Lower. If this becomes equal, then we say the integral exists. And for all continuous functions, the integral exists. If limit as x tends to infinity of L is equal to limit n tending to infinity of u, then the limit value is called as the definite integral. And it represents the area, and geometrically it represents, okay, and geometrically I will write integral a to b f of x dx represents the area bounded between the curve y equal to f of x comma the x-axis and the lines x equal to a and x equal to b. So what's happening is this limit n tends to infinity sigma I equal to 1 to n f of ci. C is any point in the subinterval, point of minimum, to delta xi. Limit n tends to infinity sigma I equal to 1 to n f of ci bar delta xi. Now what happens is this sigma represents summation of finite number of terms. This sigma looking like this, tilted m. So this sigma is used, this sigma sign is used for summation of discrete terms or finite number of terms. But then when number of terms becomes continuous and infinite, then this sigma is replaced, this expression is replaced by integral. This sign represents summation. So this sign, integral sign, represents summation s. It is an elongated s. It represents summation over a continuous interval, not a discrete. And then this, so this is replaced by integral, and this term is replaced by dx. Dx represents to differential, very small increment in x. So that is how this whole expression is denoted as integral f of x dx, summation of f of x into x, a to b. Another more, so this is the lower integral sum, this is the upper integral sum as n tends to infinity. That is what is called as the definite integral, and the definite integral is the area bounded. So another simple way of understanding definite integral now, apart from this classical definition of lower integral sum and upper integral sum, is a very simple understanding. Now that we understand what is an integral, now let us say this is x equal to a and this is x equal to b. Now this is any point x, that is distance of this point from the origin is x. Now I take a very fine differential strip, a very thin strip. It's a straight line. I'm carefully drawing it. So it's a small differential, very tiny, whose length is dx. It's differential strip, so we can ignore it, that it is of a significant length. However, here the difference between the two function values will almost be the same. The difference is almost negligible. That means the function values at x and x plus dx are almost the same. So now when we expand this particular strip, because it is thin, we can equate the strip to a very thin rectangle. So this height is f of x, and this width is dx. So this area is height times width of a rectangle. It is f of x dx. Now summation of all such strips from this point A, x equal to A to B, all such infinite strips continuously, if I sum it up, I get this area under the curve. So that summation is represented by this integral sign, and A to B is the limits, the lower limit and the upper limit. So this is the concept of integration. This gives the area under the curve. This is the definite integral. So I hope you get a very clear picture of what is definite integral. Now we did antiderivatives in the previous discussion, in the previous unit, and now we are discussing definite integral. Now definite integral we introduced as the area under the curve. It is integration, means addition, adding up. So we have added up all small strips of infinitesimal dimensions from one end of the interval to the other end of the interval to get the area bounded by the function and the x-axis. Now how is definite integral related to the indefinite integral? So this is the classical way of finding the integral, or we call it as finding the integral by the first principles. Just like we have finding derivatives from the first principles without using the formula, directly finding the derivative by limit h tending to 0, f of a plus x, a plus h minus f of a by h. So that gives derivative at a. That is derivative by first principles. This is called as integrating by first principles. Calculating something like this, just like we found the area of the circle by integrating all the areas of the triangle. So that is a standard known form, so we could relate to it. In the same way, we can find the areas of the curves from A to B. So this is the concept of definite integral. But how do we link it with the indefinite integral? So that is the fundamental theorem of integral calculus. That which relates the indefinite integral to the definite integral. Okay. So fundamental theorem of integral calculus. So if f is a continuous function, small f is a continuous function on a closed interval a comma b, and capital F is any antiderivative of f. Any in the sense you have the integration constant c. So so basically f, I'll write here. So basically f, capital F, is integral of small f. So plus c. So f is any antiderivative of f. So it includes c. So f is any antiderivative of small f on closed interval ab. Then the definite integral of function from lower limit a to the upper limit b is the antiderivative value at the upper limit minus the antiderivative value at the lower limit. This is the Newton-Leibniz formula, and this is the first fundamental theorem of integral calculus. Okay. So this result, which is a theorem derived by Newton and Leibniz, this related the antiderivative to the definite integral. All right. So that's how definite integrals are calculated. So in this first paragraph of the notes that I'll be giving to you, this is talking about the integral as the sum of all the individual components in a simplified definition. It's a simplified definition. I didn't go into detail there, but I've explained here in the class. So this is the Newton-Leibniz formula, or the first theorem of integral calculus. Now there are other theorems and corollaries. Now if f is a continuous function and this extension, just a second. Yeah, this theorem is an extension to the first one. Here instead of b, if it is a variable x, that means, let's go back to the figure. I am not integrating up to a fixed point B. I am integrating up to a variable point X. As I keep changing X, I find out what will be the area. So that gives us the antiderivative. So if f is if it's continuous on closed interval AB, and capital F is integral a to x of small f of t dt, this is denoted as a function f, capital F. So this particular function, because it will be, if antiderivative is known, then it is antiderivative at x minus antiderivative at a. So that we are writing as capital F. Now this is, because it is an antiderivative, it is differentiable at every point x in closed interval AB, and the derivative of this function, it's double implication, the derivative of capital F of x is small f of x. So this is again a fundamental theorem of integral calculus. So this is the way of actually writing the antiderivative of a function. Okay. Now, existence of antiderivatives of continuous functions. If y equal to f of x is continuous on open interval AB, then there exists a function capital F of x whose derivative on closed interval AB is small f of x. Okay. Only requirement for antiderivative to exist is that the function should be continuous. So that is theorem 2. The last one, which is a very important one, and then we go for discontinuous functions, and then 1 or 2 examples, and we close for the day. Tomorrow we'll do properties of definite integrals and a number of problems. Now this is Leibniz rule, and number of problems come in GATE on this, directly on this form. So just a second, it's getting stuck. Yeah. So let some y of x be integral f of t dt from u of x to v of x. So both u and v are differentiable functions. Then dy by dx derivative is, substitute the upper limit into f of v of x times the derivative of the upper limit v dash x, that is d v by dx, or we can write like that, minus f of, substitute the lower limit times the derivative of the lower limit. So these three, so this is a very important rule, a very important formula. And this is very simple. You can prove this by the first law. If capital F is your antiderivative, then f of b minus f of a. This is from the first theorem. Now, if you differentiate this by chain rule, you will get f dash v of x into v dash x, f dash u of x into u dash x. That f dash v of x is nothing but small f of v of x, and this is small f of u of x from the second theorem. That's it. So this is a very simple and straightforward result. Okay. So now application of theorem 1 to discontinuous functions. So if the function is discontinuous, what happens? How to find? So far we say if the function is discontinuous, continuous on closed interval AB. Now let us say function is discontinuous first at the right limit. That means at the upper limit of the interval. So integral a to b f of x dx will become, the lower limit remains as it is, lower limit is capital F of a. For the upper limit, limit x tends to b minus f of x. So you find the antiderivative. Don't substitute x equal to b in the antiderivative because function is discontinuous at b. So antiderivative in the antiderivative function, you cannot just substitute x equal to b. All right. When the function is discontinuous at x equal to a, then we do this, f of b minus limit x tends to a plus f of x. Now, if the function is discontinuous and in between value, then what do we do? Integral a to b f of x dx is this, which means integral a to b f of x dx is limit x tends to c minus capital F of x minus f of a, the first term, plus capital F of b minus limit x tends to c plus capital F of x, because the function is discontinuous. If the functions were continuous, this limit and this limit will be equal, they cancel, you will get capital F of b minus capital F of a. So if there is a discontinuity, then while computing the area, we need to go from the left hand side to the right hand and from the right hand side to the left hand if there is discontinuity. So it's a very simple and straightforward point. It's not difficult to understand. Now we will take up examples to understand how to compute limits, these integrals. And very interestingly, if you know graphs, again, if you know graphs, many times mentally you can solve. Mentally you can solve this. So let me take an example. Example of the function. These are very important examples. So integral 0 to pi by 2 sine x. What's its antiderivative? Antiderivative of sine x is minus cos x. Okay. Now we write like this. There's the antiderivative and we have to apply the lower limit and upper limit. So we write like this, or we just draw a line. Okay. Sometimes we draw a line like this. Just a line like this and write lower limit and upper limit. Now substituting. So minus f of b. So minus cos pi by 2 minus of minus cos 0. Now cos pi by 2 is 0 and cos 0 is 1. So minus of minus 1 is plus 1. So area integral 0 to pi by 2 sin x dx is 1. All right. I'll just show you the graphs now very soon. What is integral 0 to pi by 2, sorry, 0 to pi? Sin x dx.
Zero sum.
It is minus cos x from 0 to pi. That is minus cos pi minus of minus cos 0. Cos pi is minus 1. So minus of minus 1 is plus 1. And minus of minus 1 is plus 1. So answer is 2. Integral 0 to pi sin x dx. The answer is 2. Now look at this. Integral 0 to 3 pi by 2 sin x dx. Integral 0 to 3 pi by 2 sin x dx. Minus cos x from 0 to 3 pi by 2. So minus cos 3 pi by 2 will be 0 again. Answer. This is 0. Minus of minus 1 is plus 1. Again, you'll get 1. Next, the last one. Integral 0 to 2 pi sin x dx. Integral 0 to 2 pi sin x dx. What will this be? Minus cos x from 0 to 2 pi minus cos 2 pi minus cos 0. So this is minus 1 minus of minus 1, which is 0. Integration is a matter of adding areas. So let's look at the sine graph. So this is the graph of sine x. We want it in this interval 0 to 2 pi. Okay. I'll expand this. Yeah. When we did from integral 0 to pi by 2, we had got this area. We got this area, and that area was computed to be 1. Okay. We found that area to be 1. All right. Now, when we did 0 to pi, now that's a symmetric area. Exactly, the figure is symmetric. So there's a symmetry. This half is symmetrical to this half. So this area is 1. So this area is also 1. 1 plus 1 is 2. Okay. Now, when we did from 0 to 3 pi by 2, so we are integrating 0 to 3 pi by 2. Now, what's happening? We are this portion, and this portion. I will mark with a blue color now. Now, this segment is also similar to this segment. So area will be 1, but because the function values are negative, this f of x is negative and dx is positive. So f of x dx will be a negative number in this region, in this region. All right. So we get numerically this area is same as this area. So this area we got +1, here we got +1, here we got -1. So when you add up 1 + 1 - 1, you will get 1. So that's what we get this as 1. All right. And when we do integral 0 to 2 pi, then we have 0 to pi by 2, 0 to pi, 0 to 3 pi by 2, 0 to 2 pi. So this area is also included. Now, this portion of the area, this segment of the area will also be -1. So the upper area is +2, the lower area is -2. So we are calculating integrals. We are not calculating the actual area. When we talk about area bounded by the figure and the x-axis, then we have to take a modulus and we have to say this is 2 + 2, 4. The area of the entire shaded region is 4. But when we are saying integrals, in this case, from 0 to 2 pi sine x dx, this will be integral 0 to pi sine x dx plus integral pi to 2 pi sine x dx. This portion will be positive and this portion will be negative. So first portion is positive, you get +2. Second portion is negative, you get a -2, and the sum is 0. So when you say definite integral, it is the algebraic sum of areas. So this is also a very conceptual point. But when we have to find the area bounded by the curves, we have to take modulus. But if we have to find integrals, we have to take into consideration the sign. The regions above the x-axis will have positive sign and the regions below the x-axis will have negative sign associated with them. So we'll have to algebraically add those areas, including the signs, to get the value of the definite integral. So if there is a function like this, okay, all right, no problem. Suppose there is a function like this. This is the point A and this is the point B. Now, these regions will be positive. And so I will mark with a positive sign. And these regions will be negative. So when you do integral a to b f of x dx, it is equal to the algebraic sum of the areas. Okay, is this clear? This concept? So today we spent a lot of time in just understanding the concept of definite integral, and these are very vital concept not to be taken lightly. It is you will solve so many problems mentally just by uh, this particular example. If you understand what the definite integral means, just a second. Oh, unship the whole thing. Okay, I'll do something more. All right, any questions on this? Anyone has? Before we close for the day?
I have a question.
Yes.
So usually we understand like differentiation as like when we do dy by dx, we get the tangent to a point of the
Yes.
function as that.
Yes, it's
So
a slope.
integration is understood as the sum. I did not quite understand that.
In fact, differentiation in numerical methods, you will see the differentiation is treated as a difference. Of course, the difference differentiation is treated as change in y by change in x. It's the ratio of the difference in the y coordinates over a small interval, delta x. All right. What is the change in the y coordinates? So integral is the reverse. Within this particular interval, we are going on adding. We are not just taking the difference, we are adding. So in that sense, integration is the reverse process. What derivative actually gives us is the slope, the rate of change of y for a small increment in x. However, when we say indefinite integral doesn't mean anything, meaning it is just an antiderivative. But when you say definite integral from one limit to the other, then it is adding up of all elemental areas. Okay, do you get that?
Yes, sir. So regarding this, I also had one more doubt. Like in physics, suppose we are asked to integrate the function, like we are given dx by dt is equal to something. And then usually they say the procedure is you take dx, you take dt that side and you integrate both sides, you'll get x equal to something.
Yes.
So in that, is it an indefinite integral or is it a definite integral?
No, if you're finding just like if you're finding velocity function is given, and if you integrate it indefinitely, you get a displacement function with an arbitrary constant. But that arbitrary constant has to be found. It cannot be just left arbitrarily there. It has to be found, arbitrary constant. Okay. You have to put one condition, time t equal to 0, the displacement was here. So you get the value of that constant. Okay, when we do differential equations, that is what the culmination of differentiation and integration, the application is in differential equations. That's the whole crux of integral calculus. All right.
Yes, sir. Thank you, sir.
Okay, I would want all of you to go through this. I will try to upload this video within it'll take some time just to get uploaded. So within an hour, I'll try to upload it. More, you can just review these notes and also try to see the video if necessary. Tomorrow's class will be on properties. It's very, very interesting and useful, and how we can solve apparently difficult problems just very simply by using properties. All right. Thank you very much.